In this video, we're going to discuss how to write a cart tree as an equation. Now, the reason this is important is because the ability to write cart as an equation helps you to understand how things like linear effects, nonlinear effects, and interaction terms are handled in cart, as well as some more advanced machine learning algorithms that use cart as its foundation. And this includes stochastic gradient boosting, RandomForests, Mars, ISLE, and RuleLearner. Now, the key component involved in writing a cart tree as an equation is an indicator function, which I've defined here. So basically, if x is true, then this entire function takes a value of 1, and if x is false, then this function takes a value of 0. And as we're going to see, indicator functions turn out to be quite useful because they can be used to define a path from the root node, which is the node at the top of the tree before any splitting has occurred, all the way down to a terminal node. So here's our first example with just 2 nodes. Sometimes this type of tree is called a stump because there's only one split. Now, the first thing we're going to do is we're just going to look at terminal node 1, which we can see in this purple box. So if we were to just write terminal node 1 in words, all we would just say is if Rm is less than or equal to 6.94, now this condition comes from here. This is the split in the tree. So if this is true, then the predicted value is simply 19.934, which is the average here. Now if we were to write this mathematically, we would write I of Rm less than or equal to 6.94 multiplied by the predicted value of 19.934. Now to show you that that's equivalent, let me give you an example here. So if Rm were 5, without using this equation here, we can just go down the tree. So if Rm's 5, then just go to the left because it satisfies this condition, and then the predicted value would of course be 19.934. Now mathematically, if you were to write that, you would just first plug in this 5 into this Rm, so then we have 5 less than or equal to 6.94, and then you ask yourself, is that true? And of course it is. So this is true, so then the entire function here takes a value of 1. So then we have 1 multiplied by 19.934, of course equals just 19.934. So the first part of our equation for our tree is just going to be this piece. But of course, we have 2 nodes here, so there's going to be another part to this tree. And so now we're going to do the same thing for terminal node 2. Now to describe it in words, so if Rm is greater than 6.94, then we have the predicted value as 37.238. So we can see the condition here, which we see here, and also our predicted value, of course, is listed as the average. Now mathematically, we'll still express that in a similar manner to how we did for terminal node 1. We're just going to replace the indicator and predicted value. And as an example, of course, if Rm were, say, something like 8, then plug in 8 here for Rm, and then ask yourself, is 8 greater than 6.94? Well, it is, so that's true. So that means this entire function has a value of 1, multiplied by the predicted value gives you the predicted value. So the second half to our equation here is then just going to be this piece. And this actually is the equation of our cart tree. And that's it. That's how you express a cart tree as an equation. Now just to give you an example of how this works, so let's go back to this example again. So if Rm were equal to 5, then we have 1, because we plug in 5 here for Rm. So is 5 less than or equal to 6.94? Of course it is. So that's 1 multiplied by 19.934 plus, now plug in this 5 again over here. So is 5 greater than 7? No. So that's false, so that means this whole function takes a value of 0, which we see here, multiplied by the predicted value, of course, just gives you 19.934. which is exactly what you would do if you're just following the tree informally. So this is how you write a cart tree as an equation, and what we'll do now is we're going to go into a slightly more complicated example. So the first thing to note is that we have three terminal nodes here. Terminal node 1, which has a predicted value of 23.35, terminal node 2, which has a predicted value of 14.956, and terminal node 3, which has a predicted value of 37.238. Now, ask yourself, what is the predicted value if Rm is equal to 6.5 and Lstat is 15? So what you would do is you just go down the tree. So Rm is equal to 6.5, so we're going to go left because that satisfies this condition. And then Lstat is equal to 15, so we're actually going to go right because it satisfies this condition, because Lstat now is greater than 14.4 because it's 15, and so our predicted value here is just 14.956. To express this tree as an equation, what we're going to do is we're going to, just like we did before, we're going to look at the path from the root node, which is here, all the way down to each of the terminal nodes. So in our case, it's going to be from the root node all the way to terminal node 1, and then from the root node again to terminal node 2, and finally from the root node all the way to terminal node 3. So the first path we'll look at is from the root node all the way to terminal node 1, which we can see defined by this purple line here. Now again, the way we want to write this is through indicator functions. So the first part of our equation for our cart tree is going to be 23.35, which is our predicted value in our terminal node, multiplied by the indicator function for the first condition, which is here. This Rm is less than or equal to 6.94. The less than part got cut off by the line, but it's less than or equal to. Multiplied by I of Lstat less than or equal to 14.4, which is what we see here. So both of these conditions have to be satisfied in order for the predicted value to be 23.35. And this is the exact same thing we did in the previous example, except for now we just have more nodes. Okay, the second path is this orange line. In a similar manner to before, we're going to take the predicted value for terminal node 2, and then we're going to multiply it by the indicator functions that lead you down to terminal node 2. So in this case, it's still going to be Rm is less than or equal to 6.94, which is actually what we have up here. And that's just because both of these paths, at least initially, go through this same node. But the difference is going to be, instead of Lstat being less than or equal to 14.4, which would take you here, it's now just going to be greater than 14.4, which is here. So if both of these conditions are satisfied, meaning they're both true, then the predicted value will be 14.956. And finally, we'll go to terminal node 3, which is just the path from the root node here. And this is actually only defined by one condition, so this will be the predicted value in the node, which is 37.238, multiplied by the appropriate indicator, which in this case is just Rm greater than 6.94. Okay, so what we'll do now is we'll just go through this example one more time. So what is the predicted value if Rm is equal to 6.5 and Lstat equals 15? Well, the first piece is just going to be 23.35, and 6.5 is less than or equal to 6.94, so we have a 1 here. But Lstat, which in this case is 15, is not less than or equal to 14.4, so we're going to have a 0 value. Now, we still have 14.956, and what we'll do is we'll plug in our 6.5 for Rm, and that satisfies this condition, so we have a 1. And then we'll plug in now 15 for Lstat, and that actually is greater than 14.40, so we'll have a 1 here. And finally, we still have our 37.238, but in this case, rm is 6.5, and 6.5 is not greater than 6.94, so we have a 0, and our final value will then just be 14.956. So our final equation for our cart tree is here, and as you can see, you can use that directly to obtain any predicted value as if you were just going through the tree informally. Now, more generally, one way to think of these cart trees is just a function of the branches. So this is the tree from the previous example, and one way to look at it is just, if you look at this purple line, this really just defines one branch. Now this branch has this equation here that we see on the top, and so on for the other two. But if you think of cart in this way, just as a sum of branches, then a more general formula for cart is just branch 1 plus branch 2 all the way to branch k for k terminal nodes. So that concludes our video on expressing cart as an equation, and in our next video we will discuss how cart handles interaction terms using the framework that we've just developed here. If you have any questions, then please feel free to contact us at support@salford-systems.com, and I will see you in the next video.